All right, so today we're starting section 2.5, which is rational functions. So first off, what is a rational function? A rational function is a function in the form r of x equals a of x over b of x, where both a of x and b of x are polynomials themselves, and b of x can't be 0 because we can't divide by 0. So if you look at what this actually looks like, it looks like a fraction, right? So y equals a fraction, f of x equals a fraction. So we're going to get started with one right now. This is example 1. Graph f of x equals, then it gives us a function on our calculator and sketch below. So I already have it typed in on my calculator, or I did. Hopefully it didn't disappear. Maybe it did. Hold on. Y equals, it cleared already, so I'll just retype it. No big deal. Parentheses, 1 divided by another set of parentheses, x minus 1, quantity squared. I'm going to close the parentheses, and then it's plus 2 to that and hit graph. All right, as you can see what's happening here, you can see that the graph's like leveling off at a value. If you look at what value that is, that's the value of y equals 2, right? So I have a horizontal asymptote at y equals 2. Now, if you also notice that it looks like you have two branches here. And if you look, the branches do look like they're gliding up vertically along amongst a number also, and that is x equals 1. So we also have a vertical asymptote at x equals 1. So now from here, just to sketch, if I just want to get at least 1 point right, I could do that. I can plug in 2. That's a value to the right of the vertical asymptote, and I see that I get 3. And if I plug in 0, I'll get 3 also. So I can get rid of this calculator. We don't need it anymore. And then you can just graph your two branches right here. And this is what it looks like. Remember, it's got to follow along those asymptotes and get closer and closer and closer to them. Never cross them, never touch them. So here it says look at the table, but since we've learned about limits, we don't have to look at the table. We know how to fill this out without the help of the table. So it says look at the table on the calculator. When x approaches 1, what happens to the values of f of x? So let's approach 1. So if I approach 1 from the left, if I approach 1 from the right, notice they're both pointing upwards, right? So you're approaching infinity from the left, infinity from the right. So your limit as x approaches 1 is infinity, okay? Or remember, we technically could say that the limit as x approaches 1 of the function does not exist because infinity is not a number, right? So there's no value that it's approaching. Okay, so now it says, now look at your table again. We don't have to. We can look at the graph that we just made. We did a really good job of that. When x approaches infinity, what happens to the values of f of x? What about when it approaches negative infinity? So it's asking the end behavior. So as my x values get smaller and smaller and smaller, what's happening to my y values? They're leveling off at 2. As my x values get bigger and bigger and bigger, what are happening to my y values? They're leveling off at 2. So there's your end behavior for both of those. Okay, so what we just talked about was horizontal and vertical asymptotes. So my first bullet point here says if x is approaching infinity or x is approaching negative infinity, the values of f of x approach to fixed number L, which is the line y equals L, and it's a horizontal asymptote of the graph. If x approaches some number c, and the value of the absolute value of x is infinity, then x equals c is a vertical asymptote. So those are a few things that we know here. Okay? All right. So also recall that vertical asymptotes are called infinite discontinuities. Just as a reminder, vertical asymptotes, infinite discontinuities. Horizontal asymptotes are not called infinite discontinuities. Okay, because a graph can still be continuous if there's a horizontal asymptote. All right, graphs of rational functions. It says, 1, always find the domain of a function as your first step. So when we're graphing rational functions, the first thing you always have to do first is find the domain. The next thing you're going to do is you're going to look to see if the function has a hole. Finding that hole is always a mere second step. There will be a hole in the graph if the numerator is factorable, the denominator is factorable, and a common factor cancels out. That means that there's a hole in the function. After finding any holes in the graph, you're going to use your simplified rational function to find the intercepts and asymptotes. It can be done in any order. Okay, so remember to find x-intercepts, set y equal to 0 and solve for x. To find y-intercepts, set x equal to 0 and solve for y. The graph of vertical asymptotes for each, the graph of f of x has a vertical asymptote at each real 0 of the denominator. So what we're going to do to find vertical asymptotes is we're going to set the denominator equal to 0 and solve. Okay, because that's what x cannot be. Note, the rational function must be in lowest terms before you can find the vertical asymptote. Okay, so meaning since this is not simplified and factored, we can't just say that there's a vertical asymptote at x equals -2 because there's actually a hole at -2 comma something. Okay, and then it says the last set of bullet points here is that the graph has at most one horizontal asymptote. So there could be a horizontal asymptote. How do we decide if there's a horizontal asymptote? What you're going to do is you're going to compare the degrees. If the degree in the denominator is greater than the degree in the numerator, so if the degree in the denominator is bigger, then it's the line y equals 0. All right. If the degree in the numerator is bigger, so that was denominator bigger. If the numerator is bigger, the next one says if the degree in the numerator is the same, my bad, I read it wrong, same as the degree in the denominator, then it's going to be a ratio of its leading coefficients. Okay, it's going to be a ratio of the leading coefficients. Last, if the degree of the numerator is bigger than the degree of the denominator. So if the numerator is bigger, right, then there is no horizontal asymptote. We will learn more about this later. Okay, so really quickly to make sure that you understand this right here, I will make up just 3 problems really quickly. I'll do f of x equals, and then I'll do 2x squared plus 1 over x minus 1. G of x equals x minus 1 over 2x squared plus 1. And then h of x equals 2x squared minus 1 over 3x squared plus 6. Okay, so if I ask you to find the horizontal asymptotes on each one of these, if you look here, the degree in the numerator is bigger than the degree in the denominator. So therefore, this would have no horizontal asymptotes. Here, if you look, the degree in the denominator is bigger than the degree in the numerator. So this would have a horizontal asymptote at y equals 0. And then here, if you look, the degrees are the same. So it's a ratio of the leading coefficients. So it's y equals 2/3 for this one. Okay, hopefully that cleared a little bit of that up. All right. So what we're doing today is we are going to start by just finding the information and not graphing these, okay? So once again, the order for some of it is important. So the first thing you need to do is you have to say, what's the domain? So if you look at this, this is a fraction. So remember when we're finding domain, I asked myself, are there any restrictions? Yes, denominators can't be 0. So I'm going to say x minus 2 cannot be 0. So x cannot be 2. Think about how that looks on a number line. This is a positive 2, sorry. Can't be 2, but it can be anything less. It can be anything more. So my domain is -infinity to 2, union 2 to infinity. Now we always have to check to see if there are any holes. If you notice here, I did not ask you for any, like, what are the holes? It's because I made up 3 problems that had no holes. But let's just make sure that we are aware that these have no holes. In order for there to be holes, the numerator would have to be factorable, denominator, and then a common factor would have to cancel out. If you look at this numerator, it does factor. 2 numbers that multiply to give you 2 and add to give you 3 are 2 and 1. So x plus 2 times x plus 1. But nothing cancels from numerator to denominator. Here, not factorable at all, so no. Here, denominator is factorable. It factors to 2x plus 3, 2x minus 3. But once again, there isn't a 2x plus 3 or 2x minus 3 in the numerator. So there are no holes in any of these three problems. All right, so after holes, you move on to vertical asymptotes. To find vertical asymptotes, you set your denominator equal to 0 and solve. So I get x equals 2. You do not have to show that work again. It's just since these are notes, I want you to see where I just came up with it from. Next is horizontal asymptotes. What you're going to do is you're going to compare the degrees. Okay? Here, the degree in the numerator is bigger. So that means that there is no horizontal asymptote. Once again, we'll discuss what that means later. X-intercepts. Remember, you're going to set y equal to 0 and solve. So y is actually called f of x right here. So I'm going to put 0 equals. Then I have x squared plus 3x plus 2 over x minus 2. And I have to solve this. So remember, the easiest way to solve a fraction equal to something else is to make that other thing a fraction and cross multiply. So if I cross multiply, I have x squared plus 3x plus 2 is equal to 0. Right? Because those two cross multiplied 0. Now I have to solve this. So really quickly before I solve this, notice what I actually set equal to 0 to find the x-intercepts. I set the numerator equal to 0. Because in order for a fraction to be equal to 0, the numerator has to be equal to 0. So you can say the shortcut is setting the numerator equal to 0 and solving. All right, this is factorable. X plus 2 times x plus 1. I get x equals negative 2 and x equals negative 1. So I have two x-intercepts, negative 2, 0, negative 1, 0. Remember, intercepts are points. So make sure that you're writing them as ordered pairs. All right, my y-intercept, remember you plug in 0 for x to see what you get for y. If I plug in 0 for x to see what I get for y, if I plug in 0 in the numerator, I get 2. If I plug in 0 in the denominator, I get negative 2. So that's negative 1. So 0, negative 1 is my y-intercept. All right, let's move on to the next one. Same process, same idea. So domain, I'm going to say, are there any restrictions? Say it's a fraction, denominators can't be 0. So I'm going to say 2x squared plus 3 can't be 0. Subtract 3. 2x squared can't be negative 3. Divide by 2. X squared cannot be negative 3 halves. Square root to solve. Square root plus or minus. Square root plus or minus. Notice I'm about to take the square root of a negative number, which is an imaginary number. Imaginary numbers aren't included in domains. So since it's just an imaginary number that's restricted, it means technically there's no restrictions. If there's no restrictions, my domain is all real numbers. So negative infinity to positive infinity. All right, next, vertical asymptotes. Set your denominator equal to 0 and solve. I already did that right here, and I know that I got to this point right here, right? It just said not equals instead. So I know that, once again, I'm not going to be able to solve that because it's going to give me imaginaries, and that's because there's no vertical asymptotes. And it should make sense if the domain is all real numbers, there isn't a vertical asymptote, right? Because a vertical asymptote would imply that x couldn't be a value. Horizontal asymptotes, I'm going to compare the degrees. If you look, the degrees are the same. So it's a ratio of the leading coefficients. That was interesting. So I have y equals, and then 4 over 2, which is 2. So my horizontal asymptote is y equals 2. X-intercept, set your function equal to 0 and solve. So I'm going to set g of x equal to 0. And then remember, when I set a fraction equal to 0, just the numerator has to be 0. So my shortcut is setting the numerator equal to 0. Divide by 4, you get 0 equals x squared. Square root plus or minus, and I get x equals 0. So my x-intercept is 0, 0. Y-intercept, plug in 0 for x, see what you get for y. In my numerator, I get 0. In my denominator, I get 3, which is 0. So 0, 0. Remember, these come as a pair together. So if there's an x-intercept at 0, 0, the y-intercept has to be 0, 0, and vice versa. Okay, last one here, domain. I'm going to say, are there any restrictions? There's a denominator, so denominators can't be 0. 4x squared minus 9 can't be 0. There's two ways of solving this. You can factor it because it is a difference of squares. Or you can say there's just an x squared, so I'm going to isolate it and square it to solve. That's what I would do. So I'm going to do 4x squared cannot be 9 because I added 9 to both sides. Divide both sides by 4. X squared cannot be 9 over 4. And then now, remember, square root to solve. So I'm going to do square root plus or minus, square root plus or minus. Notice I'm taking the square root of a positive number this time, so there are going to be restrictions in my domain. I'm going to have x cannot be positive or negative. And then remember, to square root a fraction, you square root the numerator, you square root the denominator. So square root of 9 is 3, square root of 4 is 2. So x cannot be positive 3/2 or negative 3/2. Let's think about what that looks like on a number line. Here's negative 3/2. Here's positive 3/2. Can't be that, can't be that. Can be anything less than negative 3/2, anything in between those two, and anything more than positive 3/2. So my domain is negative infinity to negative 3/2 union negative 3/2 to positive 3/2 union 3/2 to infinity. Vertical asymptotes, I already did all the work for it. It's just that it says not equal to. This is going to be x is equal to positive and negative 3/2. So I'm going to have two vertical asymptotes. Horizontal asymptotes, compare the degrees. The degree in the denominator is bigger. So that is automatically y equals 0. X-intercept, shortcut is set the numerator equal to 0 and solve. So I go to solve for x and there is no x, so there is no x-intercepts. Y-intercept, plug in 0 for x and see what you get for y. If I plug in 0 for x, I have 2 over negative 9. So 0 comma negative 2/9. Okay, so that's so far what we've learned. So now we're going to say, okay, let's explore something really quickly. I want to graph f of x equals x squared plus 7x plus 12 divided by 4, and then also graph g of x equals x plus 3 in my calculator. I want to sketch both, okay? So let me pull my calculator back up here. Get there. I'm going to clear this out. Okay, so the first one, I'm going to do parentheses. X squared plus 7x plus 12, parentheses, divided by, parentheses, x plus 3. Okay. Then in y2, I'm going to graph y equals x plus 3. Now, on your calculators, if you have a calculator like mine, an 84 plus, it's going to graph both of these on the same graph paper. And I'm not going to be able to tell which one's which because they're both just going to be like graph with solid lines. So what I can do to change it on my calculator is that I can move over all the way to the left and then hit enter. So what'll happen is that y2 will be graphed with a darker line than y1. If you have a color graphing calculator, this is not an issue for you because the first one will be graphed red and the second one blue, or, two random colors. All right, you can hit graph. There's the first one. And there's the second one, which I typed in something in wrong. Hold on. 7x12 divided by x plus, I typed 3. It's supposed to be 4. Now, I knew that I typed it in wrong because I know that this was supposed to happen. They're the exact same thing, right? So I have to think about how are they different? Because if you look at them, they do not look, I don't need my calculator anymore. They do not look exactly the same, right? So I say, okay, well, what do I see? What do I notice about this? You should notice that your numerator is factorable. So let's go ahead and factor this. F of x equals, my numerator factors to x plus 4 times x plus 3. My denominator is x plus 4. So this fraction is simplifiable. I have a common factor of x plus 4 that cancels out. What does that mean? That means that there is a hole in this graph, okay? So to find out where the hole is, I'll write that down right below this. Where would have there been an asymptote if that didn't cancel out? At x equals negative 4. So the hole is at negative 4, comma. And then to find the y value, you have to simplify this fraction. So it's down to x plus 3. And now what I can do is I can plug in negative 4 right here. Negative 4 plus 3 is negative 1. So it's the line y equals x plus 3, except there's a hole at negative 4, negative 1. So let's go ahead and graph that. Negative 4, negative 1, there's a hole, right? But it's just the line y equals x plus 3 here. So y-intercept of 3, slope of 1. So this is actually what the first one looks like. And this is what the second one actually looks like. There's no hole in this one. Okay. All right, so are these graphs the same? No, they're not, because there's a hole in one of them. Does the first one have a vertical asymptote? Because at first glance, people will say, oh, there's a vertical asymptote. X can't be negative 4. No, it does not. All right. It has a hole. So it says, look at the table on your calculator when x is equal to negative 4. What is the value of f of x? So if you look at the table, let's go back to there and I hit, come on. Second table. I'm looking for when x is negative 4. So I get an error, okay? But if you look in y2, it says it's negative 1 there, okay? So what does it say? It says that there's an error, okay? What does that mean? It means that there's a hole at x equals negative 4. We can find holes in our graph by factoring and simplifying. We always write holes as ordered pairs, so you're not going to write it's at x equals negative 4. What you're going to do is you're going to find the y value. All that you're going to do is substitute x back into. Substitute x back into the simplified equation. The ordered pair of the hole that we just found was negative 4, negative 1. Okay? Remember, holes are called removable discontinuities. Okay, so if you notice what we're doing now is that we are going to just get the information to graph. Next, we'll move on to actually graphing these, but I want to make sure everyone can just get the information. So example 4 says find the hole in the function. So that's all that I actually want to make sure you're able to do. So in order to find holes, what you're going to have to do is you're going to have to factor and simplify. So I'm going to do h of x equals, do not lose the h of x equals 2 times x minus 2, because there's a GCF of 2. Also, I want to point out, because I kind of just factored that so quickly, is that a lot of times people look at this and they'll say that's not factorable. Don't forget to look for GCFs. Now I'm going to factor this. I need two numbers that multiply to give me negative 10 and add to give me 3. So that's x plus 5 times x minus 2. So you can see that there is a hole in this graph, because there's a common factor. So now I'm going to say where the hole is. The x value is 2, because that's where there would have been a vertical asymptote if it didn't cancel out. Now I always want to write the simplified function, which is 2 over x plus 5. And then I have to plug 2 into that equation. So if I plug 2 in here, I get 2 over 7. So the hole is at 2 comma 2/7. All right, let's go through everything before we start graphing, and then we'll switch to putting it all on graph paper. Okay, you have to start with your domain. It's always number 1. You must do this first. This must be done second. And then the order of everything else does not matter. I like doing it in a certain way, and I might jump around and do that. Who knows? Okay, so for my domain, I say, are there any restrictions? Yes. Denominators cannot be 0. So I'm going to solve this by adding 1 to both sides, square rooting to solve. So I have x cannot be positive or negative 1. You can draw what that would look like on a number line. I'm going to jump right into doing the domain. So negative infinity to negative 1 union -1 to 1, union 1 to infinity. So everything but -1 and 1. All right, next I'm going to see if there are any holes in the graph. So I have to say, is my numerator factorable? Is my denominator factorable? By looking at them, I can say, yes, both are. I don't know if any common factors cancel out yet, but I can see that they are both factorable. So off to the side, I'm going to do j of x equals. Don't forget j of x equals. All right, I'm going to factor my numerator. Two numbers that multiply to give me 4 and add to give me 5 are 4 and 1. So I have x plus 4 times x plus 1. And then my denominator is a difference of squares. So that is also factorable. That factors to x plus 1, x minus 1. So I'm going to say, okay, are there any holes? The answer to that is yes, because there's a common factor from numerator to denominator. So I'm going to say the hole is at -1 comma. And then now I want to write down my simplified function. Now this is the most important part, okay? This is what you are using to answer every other question. Don't ever look back at this. It's gone. It's over. Okay, you've simplified it down. So once you've found the x value of the whole, you're never looking back at the original. All right, so now I'm going to find the y value of the whole. I'm going to plug -1 into the new j of x right here. So I'm going to do -1 plus 4 over -1 minus 1. So that's 3 over -2, or -3/2. All right, now I'm going to find the x-intercept. The x-intercept, remember, I set j of x equal to 0. I set y equal to 0 and solve. The shortcut is set the numerator equal to 0 and solve. So if I set the numerator equal to 0 and solve, I get x equals -4. So I have -4, 0 as my x-intercept. Notice I'm not looking back at the old one because I'm not going to say that there's also one at -1, 0, because there isn't. There is a hole in the graph at -1, -3/2. Y-intercept, plug in 0 for x and see what you get for y. So I get 4 over -1, which is -4. Vertical asymptote, set the denominator equal to 0 and solve. I get x equals 1. Horizontal asymptotes, compare the degrees. They are the same, so it's a ratio of the leading coefficients. The coefficients are 1 and 1. So y equals 1 over 1, which is just 1. Okay, so what we're going to do now is we're going to use this information to actually put this on graph paper.